In this lecture, we will talk about the concept of binary heaps. So we start with the idea of a priority queue. So what is a priority queue? Well, we talk about three things that are important: the insert, finding the minimum, and deleting the minimum. So we want to do all three operations the best way possible. If you recall, when we implemented a priority queue with an array where the first element is the minimum, we had to settle for big O of n complexity for delete min. So that seems like too much to ask, because it's sort of like if you delete n elements from this priority queue, and that would cost you big O of n squared, although we could have done inserts and finding min in big O of 1. So we're going to talk about a new data structure called a heap, which will allow us to overcome some of these things and find the best way to get the best complexity possible in terms of delete min and insert. So we talk about this idea called heap. Now heap is a data structure with two invariants. One is that it is a shape invariant. It says that it is a binary tree. What we mean by binary tree is that for each node you can have up to 2 children. I'll talk about the complete idea in a little bit. Then there's the order invariant that says that for each node, parent is less or equal to both its children. So an example would be something like this. So here the parent is 3, the children are 5 and 3. So you can have 6 here and 4 here, where the parent is 5 and children are 6, and we can't have 5, so let's make it 5 here. So this is an example of a order invariant satisfied by the heap. So when you talk about the order invariant, we talk about the parents with children, not the leaf nodes. The leaf nodes, those are the nodes at the end of the tree, are not supposed to satisfy this property. So let's talk about the heap invariants in more detail. First of all, shape invariant. If you have one node, I can have a one node heap like this. If you have two nodes, the second node must be the left child of the first node. When the third node comes, that must go as the right child of the first node. When the fourth node comes, it goes as the left child of the second node, and so on. So we can build these things, and if you name the nodes in the order they come, order they insert, it will be something like this: 4, 5, 6, 7. So idea is that this is a binary tree, which is clear. Binary means that you only have 2 children per node, and also the nodes are inserted by the level from left to right. So you can see it's 1, 2, 3, 4, 5, 6, 7. So in terms of the order invariant, you can have a number like 2 here, 5 here, 3 here. So in this case 2 is less than or equal to both its children, 5 and 3. Then you can have perhaps 5 here, 6 here, and now the 5, this element is less than or equal to both its children. Now if you insert another element, so you can have another element here, let's say that we can put something like 4, or we can put something like 5 here. So notice that the heap can have duplicates as long as it satisfies all the invariant properties, both order invariant as well as the shape invariant. So in terms of operations, the major operations for heaps or priority queues are the following. We must be able to insert, delete min, and find min in some complexity, some efficiency. So if you take a random array with min at a's of 1, which is what we talked about first, we knew that we could do insertions in big O of 1, but the delete min would cost us big O of n, and find min would cost us big O of 1. Now instead of a heap, we can talk about this new idea, because it is a tree, and we'll talk about the height of the tree, and we will say, okay, we could do both of these things in log n, and find min is still big O of 1. So since you perform many insertions and deletions from this data structure, from this applying operations, so having insertions and deletions at log n is very advantageous because it's one of the operations you perform the most. So let's talk about inserting something to a heap. So we are given a heap here. We check to make sure it satisfies the properties. The elements are filled by the levels and they are filled from left to right. You have 2 less than 4 and 3, 4 less than 9 and 7, 3 less than 8. So now let's just say if you insert 1 into this heap, now clearly it violates the heap order property, which means that 1 is now less than 3. Therefore we have to do some sort of a swap between 1 and 3. So our new heap would look like this: 2, 4, 1, 9, 7, and then you'll have 8 here and 3 here. Now still there's a violation of the heap order property here. 1 and 2 are not in the right places, so we do a swap here again, and so we will get finally 1, 4, 2, 9, 7, 8, and 3. So we know that after you insert the 1, you will have this heap here. So let's do another example of this. Let's suppose that we insert 0 into the heap. So the 0 will start here, because it'll go to the next available leaf node from left to right. And now we'll have to move the 0 up the tree. So 0 and 19 will be swapped, and then 0 and 16 would be swapped, and then 0 and 13 would be swapped. So our final tree looks like 0, 21, 13, 24, and 31, 32, 47, and then you will have 16, 68, 20, and 19. So we know that this is a complete binary tree, and also each of the parent nodes are less than or equal to its children. That's the case here. So I circle the parent nodes that we need to look at, the parent nodes that are not leaf nodes, and they're all less than or equal to the children. So that's the insertion process. So we can do this exercise of repeatedly inserting 34, 23 into a heap. So we start by inserting 34, that goes to the root, and then 34 we insert 23 as the next available location, but because 23 is in the wrong place, we would swap the two things. We'll obtain this heap. And once the 78 is inserted, so we start by saying let's insert 78 into this, and since the heap order property is satisfied, we can continue to do this. So we have next insertion would be 65. That will go to the next available location, and that's in the right place. And the next insertion is 21. So 21 will start here, but soon it'll move up the tree branches here to give you 21 will go all the way to the top, and then by swapping things, so the 23 would come here, 34 would come here, and 65 is here, and 78. Once you insert 56 into this, so we'll start with the tree, we'd start 56 here, but 56 is in the right place, we don't need to do anything there. The next element comes, and the next element 56, and the next element is 72. 72 goes here, but since it's smaller, it must move up to the 78 place. So the final heap would look like 21, 23, 72, 65, 34, then you will have 56 and 78. So this is a heap, and that's why satisfy both properties, the order property and the shape properties. shape invariants, and that's a heap there. Now deleting the minimum means that this is the minimum of the heap. If you like to delete it, what you typically do is to swap that element with the last element in the heap. This is the last element, so we're going to swap that. Now we will bring the 20 into that location. 21, 16, 19, 68, 24, 31, 65, 26, 32, 47. Now that element we swap and delete it, so it no longer exists. But the only problem is that now we will have to make sure that this is in the right place. Now it's not in the right place, since we will have to move it down. We'll have to do we'll have to exchange that with 16, and the 20 will go here, and then 20 will continue to go down to where the 19 is. So the 19 will come here, and 68 is there, and this piece, then 21, and this whole part here will be the one that you have this tree there. So the delete min is performed like that, and you can see now it's a heap, and it satisfies the heap properties. So in this case, we can continue to delete min until it's empty. Now we did delete min for one of them. You can continue this as an exercise. Let's do some analysis. Complexity of insert. The way we insert things was that when you have a heap of some n elements, so let's think about the heap of n elements. Now one of the things about the heap is that a heap has a max of 2 to the 0 element here, 2 to the 1, 2 squared. So if you define the height of this tree to be the total number of edges from root, where we define the entry point to the thing as the root, to the lowest leaf. And so in this case, if you look at the picture that I have here, the height of this tree would be 2, and we notice that the number of elements in this tree is going to be, total number of elements is 2 to the 0 plus 2 to the 1 plus 2 squared. So the total number of elements in general is going to be n is 2 to the 0 plus 2 to the 1 plus up to 2 to the power h, where in the previous case h was equal to 2. So we do know from concepts, math concepts, that this adds up to 2 to the h minus 1, h plus 1 minus 1. So n, the relation between n and the h, the height, is given by this, which implies that the height is a big O of log n. So this is one of the advantages of the heap, that your height will never be more than log n complexity. So what that means is when you insert something to a heap, the worst thing that can happen is once you insert the new element to the heap, the worst thing that can happen is that it can come down on a path all the way to the root. It can go all the way up to the root, but it can only go up to a log n height. So the complexity of insert is big O of log n. Now the complexity of delete min would be similarly analyzed, because in delete min, if we recall, what we did was we want to delete this, but we replaced that with the last element in the heap, and then we bubbled it down. So in the worst case, you cannot do worse than log n complexity. So the complexity of delete min is also log n. Find min is a very easy one, because we know the minimum is always the first one, so therefore we don't need to traverse the tree to do anything, so it can be done in big O of 1. Now complexity of building the heap. Now we know that if you repeatedly insert elements and start building the heap, then we do know that each node will take up to a log n complexity of insertions, and if you insert n nodes, each at the log n complexity, so we can expect the build heap to work at log n complexity. So that's an easy argument to make. We have n elements, each one cannot be worse than log n complexity to insert. There's also a clever build where if you have a bunch of things, random elements that are all over the place. So let's take a bunch of random things and then we'll try to do a build heap on this one here. So the idea here is you assume that all the leaf nodes are heaps themselves, and then you start with the first non-leaf node. This is the number 1. Now you make sure that 12 and 20 form a heap, which is the case. And then you go to the next node and you look at this and say, is that a heap? Since 13 and 6 are in the wrong places, then you say, okay, well, let's just swap those two things. So now you go to the 25 place and see if you want to make it a heap. So in order to make it a heap, you look at 25 and say, well, let's look at the minimum of the two things. So that's the one that should come to the top, and the 25 will go here, and the 13 is here. And now once 25 and 13 is compared, it should come down further. So you will have 6, 13, 25, 20, 12, and 20. So here's the clever build. Why do we call this a clever build? Because what we do is we do a bottom-up building of the heap. We keep doing this until the heap is completely done. Okay, so let's take a look at how we analyze the clever build process of building a heap. So what we mean by clever build is that we have a tree, a binary tree, a heap that we're building, and what we did was from the previous slide that we assume that the leaf nodes are already heaps by themselves. Look at the leaf nodes here, and then we start with the first available node at that level, and then we try to make that small tree a heap. We try to take this piece here and try to make that a heap. So in terms of analyzing things, we do know that if the height of the tree is h, let's assume that the height of the tree is h. In this case, you have a tree of height 3. There are 3 edges coming from the top to the bottom, and then we have up to 8 nodes at the lowest level. So in other words, we have 2 to the h nodes here. The one before that you have 2 to the h minus 1, and so on. At this level you have 2 to the 0. At this level you have 2 to the 1. So when you think of the number of operations that we'll be doing, we take these 2 to the h minus 1 nodes, we bring them a maximum of 1 level down. So it's going to be 2 to the h minus 1 times 1. And then if you take the 2 to the h minus 2 nodes, we bring them maximum of 2 levels down each node, and so on. So the final node, which is the we only have 2 to the 0 nodes at the first level. The worst case scenario would be that we would bring that down h levels here. So in terms of writing this as a series, we can write this as 2 to the power h minus I times I, where the I will go from 1 to whatever. So when I to 1 to h here, when h equals I, we'll get 2 to the 0, and when I equals h, you will get 2 to the 0. So what we have is this summation, and then now we have to show that this summation is indeed, we're going to leave this as a challenge to show that this summation is indeed big O of n. Now my suggestion is to really think about this as a simple integral, since we know that this discrete sum can be bounded by an integral of this form, 2 to the h minus x times x dx, where the x would go from 1 to h. So you can think of this as an integral, and you can apply the integral principles to show that this has a big O of n complexity. Now that's better than the n log n complexity that we talked about before. So we can show that the asymptotic complexity of build heap can be done in big O of n. So in terms of implementation, how would you implement this? Now one of the problems is that when you think about a binary tree, you can say I'm going to implement this as a node with 2 pointers to its left child and the right child. But this is a special kind of a binary tree. It's really a complete binary tree. So we can come up with a schema like this. We can say, let's just think about an array, and let's assume that if the parent is in the position I, then the children are at 2i and 2i plus 1. For example, if 1 is the parent, then 2 times 1 is the left child, and 2 times 1 plus 1 is the right child. If 2 is the parent, then 2 times 2 is the left child, and 2 times 2 plus 1 is the right child. So it seems like we have a unique representation in terms of representing a complete binary tree as an array. So in this case, so this shows more graphically what we're talking about. So parent at position I, children at 2i and 2i plus 1. So if you give me the parent, I know how to find the children, and if you give me a child index, I'll be able to find the parent, because if you give me 2i, once I divide I get I. If you give me 2i plus 1, once I divide by 2, I still get the I. So you have a unique parent for each child, and so on. So so we have two operations that in terms of performing heap adjustments. We call this percolate up and percolate down, or sometimes we call it sifting up and sifting down. And adjusting the heap after the insert is sifting up. So what we do is we insert 14 and then we try to bubble it up until it's in the right place. So in terms of looking at this from an array point, you can say that in an array we don't use the 0th location. So here's 13, 21, 16, 24, 31, 19, 68, 65, 26, 32, and 14. So if we're trying to move 14 up, what we try to do is 14 should go to 31 location. So if you write down the indices here, 5, 6, 7, 8, 9, 10, and 11. So what we do is we take the index 11 and divide by 2. That gives us the index 5. So we compare 14 and 31. Since 14 is less than 31, we should swap the 14 and the 31. Now then you compare the 5, you take the index of 14 now, which is 5, divide it by 2 to find the parent. So 5 divided by 2 gives you 2, and you compare 14 and 21. In this case, since 14 is less than 21, 14 would move here, and 21 would come here. So in the tree, it looks somewhat like this: 14 and 21 and 31. So the idea is the 14 would go as far as it can go. Now you have 14 has an index 2 now, but the divided by 2 gives you 1. That's your parent, but because you're bigger than parent, you would stop. So in terms of a loop, all we are doing is essentially we are given an I. We are looking at as of I. If the as of I is less than as of I over 2, then we would like to swap as of I and as of I plus 2. Obviously, looking at the boundary conditions is important. We do this as long as the I is greater than 1, strictly greater than 1. And so that's the case. But we will write the code to understand this process better. Now, if you adjusting the heap after deleting them in, you're going to sift it down. So for instance, if you want to delete 13, so what we typically do is 14 is moved here, and then we remove this last element from the list, and then we try to move the 14 down. So let's look at that process here. So let's take a look at the original thing. We have 13, 21, 16, 24, 31, 19, 68, 65, 26, and 32, and 14. So the first thing we do is we take 14 and swap it with the the top element of the root. So the 14 goes here, and this element is removed, and our size of the heap is pointing there. Now size is reduced by 1. So now what we need to do is we take 14 and we look at the children of 14, 21 and 16. We find the minimum of the two. If 14 is less than 21 and 16, we leave it there. So in this case, it is the case. Otherwise, you're going to swap it with the minimum of the two children and continue to go down. And that's what you would do in the case of sifting down the process. So this concludes the lecture on the heap, sort of the conceptual discussion. But in the next lecture, we'll talk about how we write code to accomplish what we discussed here.